All right. So, AP, today we're talking about Gibbs free energy and equilibrium. All right. So let's take a little trip down memory lane back to our equilibrium talk. Now, equilibrium, or these K values with our products over reactants, uh, if we looked at the Q quotient, we could tell whether or not we were at equilibrium, or if we were past equilibrium, or if we weren't quite at equilibrium. Okay, we could also tell whether our equilibrium was more products or reactants favored, depending on its whether or not it was above or below 1. Now, the Gibbs free energy, if we think about Gibbs free energy and what it means, if delta G is less than 0, meaning it's negative, then it is a spontaneous reaction. Okay, that reaction is going to happen spontaneously. So it would stand to reason that the K value for that reaction, that equilibrium value, if the reaction is spontaneous, it should be greater than 1. Okay, if delta G is less than 0, so if delta G is negative, then K has to be greater than 1, correct? That means that the reaction is happening on its own, which means it is driving towards the products on its own, so the equilibrium must be product favored. Okay? Now, there is a calculation that we can find equilibrium constants for reactions and delta G's and vice versa. Okay? And that is delta G is equal to negative RT times the natural log of K. All right. Now, that delta G you already know is the Gibbs free energy. R is the universal gas constant. Universal gas constant, which is 8.31 joules per mole Kelvin. Okay. Now, let me check just to be sure. Yep, we're good. So that is the equation for relating Gibbs free energy to chemical equilibrium. Okay. Now, again, a spontaneous reaction does not mean that this reaction is noticeable or even measurable in any way. Okay. Like rust, it is not measurable in a time frame of like a couple days, right? It probably won't happen in a couple days. So, what we need to think about is that if a reaction is spontaneous, meaning delta G is less than 0, that also means that K would be above 1. But if it is not measurable, it's not noticeable, that means not noticeable. That means that the activation energy, the EA, is a very high number. Okay? That's what that means. Now, back to this equation. We can solve this for the K value too. So if we have the K value and we want to find the delta G, then we could rearrange and we could say that delta G over negative RT is equal to the natural log of K. And then the natural log is canceled out by E, the exponent. And so K is equal to the exponent E of negative delta G over RT. Okay? So both of these equations can be used to find the delta G and the equilibrium constant in this situation. Okay? It's a quick video today. It's going to be a little bit more involved when we start doing practice problems and stuff like that. But and Friday is going to be a little bit more complicated. So that is it for today. Email me if you have any other questions.